All right, this is our final lecture for the semester, lecture 23 for Chem 223. Today we will be finishing up talking about mass spectrometry. So last lecture we spent talking about ionization techniques. Today we're going to talk about mass selection and detection. So there are four types of mass spectrometry we're going to talk about. We're going to start with time of flight, or TOF. Then we'll talk about quadrupole instruments, magnetic sector, and Fourier transform. Fourier transform we're actually not going to be talking about under this part 2 section. We're actually going to talk about it when we get to it in part 3 under ion detection. And hopefully it'll make sense to you why I did that once we actually talk about FT instrumentation. And then as a bonus, we're going to finish up by talking about how to interpret mass spectra. So let's go ahead and start with the TOF, or time of flight instrument. So a time of flight instrument is actually really simple. You have a tube, a really long tube. This is called a drift tube that your ions are going to fly through. So you get all your ions on one side of the tube, and then you accelerate these ions using what's called an accelerator plate, or more commonly referred to as a pusher, that pushes the ions through the tube and they hit the detector. So if we have a bunch of positive ions in here, what we'll do with the pusher, or the accelerator plate, is we will apply a positive potential to it for a very short amount of time. That positive potential will cause all of your ions to fly over to your detector. I'll let you look at that again. Notice that here we have low mass ions. These are represented as small ions here, but don't confuse size with mass. Right, we're looking at mass here, not the size of the ions. Those are two very different things. So the lighter ions are going to travel more quickly and hit the detector plate, and then the heavier ones are going to reach later. And so we can tell the mass to charge ratio of our different ions that are based on how long they take to get through this tube. Now, how do we do that exactly? Well, we have to turn to some equations we get from physics. The first is that our kinetic energy is going to be equal to 1/2 mv squared. And the second is actually a second equation for kinetic energy that says that the kinetic energy imparted to an ion is equal to the charge of the ion times the electric field it's in. Now, if you remember, we had all our ions here and we applied an electric field by putting a big potential on our pusher. And so all of our ions received some amount of kinetic energy. And that energy is equal to the charge on the ions times the electric field. Now, how do we take this and turn it into mass to charge? Well, we're just going to start by setting these two equations equal to each other. So we have QE equals 1/2 mv squared. That's just these two equations where we've substituted the expression for KE from one equation into the other equation. And then we can also remember that velocity is equal to distance over time. So this is how far you travel in a given amount of time. Our distance that our ions are going to travel in our drift tube is just equal to the length of our drift tube, represented by an L up there. And of course the time is just the time. So we can substitute V in this equation for this L over T. And then all we have to do, we have a mass term here, we have a charge term here. We'll divide charge over here. We'll divide everything else from this side over onto that side. So we get this equation for mass to charge, which is just equal to 2 times the electric field that we put on our accelerator plate times the drift time of our ions through the tube divided by the length of the tube squared. So all ions in this device receive the same kinetic energy per charge. So if you double the charge on an ion, you just doubled the amount of kinetic energy that ion is going to get. That's why it's not just the mass here that determines the flight time through the detector, it's also the charge. So if you increase the mass, you're going to increase your drift time, and if you increase the charge, you're going to decrease the drift time. So then we determine the different mass to charge ratios based on that flight time. So we can't determine mass alone or charge alone. We can only figure those out as a pair. Though we can actually figure out how many charges are on an ion based on how far apart the isotopes are, because if your ion has a single charge on it, the isotopes will be 1 mass unit apart. If it has 2 charges on it, the ions will have a distance or a difference of a half mass unit in between them, etc. On time-of-flight instruments can usually resolve masses to 1 or 2 decimal places, so it's usually pretty good, especially for analyzing small molecules like drugs or anything they make over in the OChem lab. Usually you take between about 2 and 8 spectra per second. Our instruments in our lab usually take about 4 spectra per second. I currently have 2 time-of-flight instruments in my lab, and in our building, the Benson building, I believe we currently have 4 or 5 time-of-flight instruments. And these guys, when you design them to work really fast, you can actually collect a spectra every 200 microseconds. So that's about 5,000 spectra per second. And usually you're limited to a mass range up to about 4,000 mass to charge units, but with time-of-flight instruments, you can actually go up to as large as 500 mass to charge units, or as high as 500 mass to charge units. And some Chinese scientists have actually been able to use this to measure intact viruses. So they sent viruses through using electrospray ionization, got it to the time-of-flight instrument, and were able to measure the mass of individual viruses, which is pretty cool. All right, the next instrument we're going to talk about is the quadrupole mass filter. So in a quadrupole, quadra means 4 and pole means pole. So this literally just means 4 poles. So we have 4 poles, and right here I have a kind of a side view looking at the 4 poles. So you send your ions in from this side, and whatever makes it through this quadrupole mass filter hits your detector and you can see it. And right here I have a front-on view. And what's going on is the poles that are opposite of each other are paired. So you have 2 positive poles and 2 negative poles here. And then what you would do is you apply an RF frequency through each of these poles and a DC potential through each of these poles. So you're actually applying the RF and DC at the same time. And so at any given time, these positive poles have the same RF and DC potentials on them, and these negative poles have the same RF and DC potentials on each other, and usually the RF and DC potentials on the positive poles is the opposite of what it is on the negative poles. Okay, so that's a lot of information. Let's go through it a little more slowly and give some implications of it. I'm going to get rid of most of this from my slide. We'll start by talking about the radio frequency. So if you don't remember, a radio frequency is just an alternating frequency or an alternating potential here. And so for some amount of time, the positive poles have a positive potential on them from the RF frequency. And for some amount of time, it's negative. So it's positive and then drops down to be negative. And the negative poles are doing the opposite of that. And what does that actually do to our ions as they go through here? Well, our ions are going to be trying to chase the potential they're interested in. So let's say these are positive ions. They're going to be chasing the negative potential, right? And so as they're traveling towards this pole, if it's got a negative potential, as the ions are traveling towards it, we'll then take the negative potential off that pole, we'll make it a positive pole and make this one a negative. And so these ions are always trying to get to the negative potential. And the ions all circle at about the same rate, so their frequency that they're spinning around here is about equal to the RF frequency we're applying on these poles. But lighter ions, if you'll notice here, we have the heavier ion in the middle and the lighter one outside. The lighter one is able to travel more quickly, and so it actually gains a larger orbital radius as it's chasing that potential. And if it's too light, it can then fly into one of the poles and get stuck because its orbital radius is big enough, it's traveling fast enough that it caught that wave. Woo-hoo. All right, so the RF frequency, or the RF potential, destabilizes light ions. So all of these ions are traveling straight through these poles towards the detector, and they're trying to get there really fast. And so what we're just seeing is kind of a snapshot in space as they're moving towards the detector. All right, so we have the RF going, and at the same time, we actually have a direct current or DC potential on. That just means a flat potential. And this is why we label some of these poles as positive and some as negative, even though we're sending an RF frequency through there that makes them positive and negative at different times. These positive poles are actually always positive, or not always positive, but they always have a positive offset from zero, and the negative poles always have a negative offset from zero. And so what's actually going on here, I'm just showing the DC potentials here, but with the RF stacked on top of that, it actually looks more like this as we go through time, and the negative one, of course, looks like this. And so you have the DC and RF potentials going at the same time. Now, this animation that I'm going to show of the ions here isn't perfect because I really don't know how to make a perfect animation here. But what happens is this offset in these potentials actually makes these orbitals not round. The ions aren't orbiting in a round shape. They actually become a more oblong shape or egg shape or oval shape. I guess they're not really egg shape. They'd have to be oval shape because there's no way of getting an egg shape in here. But if that oval shape gets stretched out too far, then the ions are going to impact the negative poles. And of course, if we're sending negative ions through here, they're going to impact with the positive poles. And then anything that's light enough that's not going to hit those poles, their oval orbital will be stable enough and they can make it all the way through this quadrupole and collide with the detector. So our heavy ions here are destabilized by the DC potential. Okay, so let's sum all that up. Our RF destabilizes the trajectories of the light ions, and the DC destabilizes the trajectory of heavy ions. So we add those two effects together to actually select out a narrow range of ions. So there's a narrow range of mass to charge in here. And then what we can do is we can vary the RF and DC potentials so that we actually change which mass to charge window we're letting through here. So then basically we just scan through the mass to charge range and build a mass spectrum that looks like this. It's a pretty fun technique. It's pretty complicated, but it comes together to give a nice triangle, which is fun. Triangles are always fun. Here is a picture of an actual quadrupole instrument that was taken out of an instrument a few years ago here. And here is the front view of this quadrupole. You might recognize this as the image from the title slide here. And so the ions fly down through this hole, and these poles try and destabilize everything we don't want from getting down that hole. Now, quadrupoles actually have really terrible resolution. You can usually only get at best about 1 AMU or 1 Dalton. So an atomic mass unit is equal to a Dalton, which is equal to 1 gram divided by Avogadro's number. And with a quadrupole, though, it can be really difficult to separate some species like C6H10 and C5H8O. Both have really similar masses, as you can see from the video here. And so they can actually be pretty hard to separate by quadrupole. And so what we usually use quadrupoles for is as pre-filters or as pre-mass spectra or mass spectrometry experimental devices before a more sensitive device. So what you can see here is an instrument where we have 1, 2, 3 quadrupoles coupled to a time of flight instrument. So right here it looks like there might be 2 separate quadrupoles, but they're actually coupled together too. And so what you do usually is you use this first quadrupole to select for an ion. You use the second quadrupole to cause some amount of fragmentation. Usually you have your ions fly through there really fast with a bunch of background gas. And so your ions will collide with the gas and break apart. And then in the third quadrupole, you can select for different things, either a window of fragments you want to look at or specific fragments, or you can fragment a specific fragment. And then that can go into your time of flight instrument right here. And here I actually have a time of flight tube that has a mirror, and so sometimes this happens where your ions will fly down, and then you'll have another potential down here that bounces your ions back up to your detector. That way you basically get double the path length without doubling your tube length. So these can be as much as 4 or 6 reflections before you get to the detector, and so you can get long path lengths. Right, the last of these instruments we'll talk about before talking about detectors is a magnetic sector instrument. So in a magnetic sector, what you have is a strong electromagnet here. And if you don't remember, an electromagnet is a magnet you create by sending a current through it. And so electromagnets are nice because you can change the strength of the magnetic field just by changing the amount of current you're sending through here. But you'll send your ions in from your ionization source in through the electromagnet, and just a fundamental principle of physics is that when an ion goes through a magnetic field, its trajectory turns. It actually tries to orbit the magnetic field, but in a magnetic sector instrument, we design this so that it can't really turn enough to orbit anything. It usually just gets through about a half a turn here and then flies into a detector. So light ions will be deflected more by that electromagnet. Heavy ions will be deflected less. And then we have a slit here that we use to control which ions get into our detector. So if the slit is really narrow, we can let through a really narrow range of mass to charge here to get to our detector. If we make it big, we can get more ions going through there, right? So then what we usually do after we have our slit and detector set up is we'll sweep through our magnetic field strengths. So when we're at a low field strength, only our light ions will hit the detector. As we get to a medium magnetic field strength, mid-range ions will hit the detector. Higher range, or a higher magnetic field, then our heavy ions will hit the detector. And I'm talking about that as if we can only get 3 groups of ions going through, but we can actually get pretty good resolution in this technique as well, down to 1 or 2 decimal places. And if you're really careful and have a high concentration in your analyte solution, you can get down to 3 decimal places sometimes. But the real limiting factor here is that as you lower your slit width to get better and better resolution, you're also decreasing your signal. Similar to in UV vis, when you change your slit lengths or slit widths, you're going to, with your lower slit widths, you'll get higher signal, but worse resolution. With lower slit widths, you'll get more resolution, but lower signal. Here I have the picture of the quadrupole again. Let's go to the next step, which is our detector. So detectors for these instruments, these first 3 that I've talked about, are pretty simple, and they look a lot like photomultiplier tubes. So right here is a schematic diagram of what's called a discrete dynode ion detector. And this is almost exactly the same as a photomultiplier tube, except in the first step, you don't have an electron or a photon interacting with some sort of metal with a low work function. Here you have your ion colliding with some material that lets off electrons real easy, and then you have that collide with more plates going down, and then finally to a transducer that sends your signal to your computer. So again, you have your ion collide with this, that frees up some electrons because your ion's hitting it with a lot of force. Then you have this plate as at a slightly higher potential, so those electrons will come and hit it, and so forth and so on. I said that phrase backwards, but that's life. Now this is one type of detector we can use. We can actually get a lot more electrons, or a lot heavier flow of electrons, if instead of having discrete plates, we make a continuous dynode. And the way we do this is we basically have an open tube made out of a resistive material, and we apply a potential from the top to the bottom. So up here we have a low potential, and that potential gradually gets higher, and it gets really high towards the end. And so if an ion comes and collides in here and frees up some electrons, those electrons will come hit this part of the tube, and they'll bounce off, and they'll just keep trying to bounce from spot to spot on the tube, trying to get to a higher and higher potential because electrons like high potentials. And so by the end, you can have sometimes hundreds of collision events down here, and you get just tons and tons of signal off of this type of device. And so often people will ask, well, doesn't that lower your resolution because you get this big cloud? Sort of, but the electrons here actually flow way, way faster than the ions coming in here. And so all of these electrons can flow through for a single ion before another ion hits often. And often, of course, these ions are hitting in big packets full of millions or billions of ions all at once. So you have this huge sea of electrons flying down there. But usually you have your analyte come hit some material. It's often a copper and beryllium mixture that releases your electrons and starts that cascade. So here is actually another picture of that quadrupole where the ions are set to collide with this copper beryllium surface here. And then the electrons that get freed from that can come down into this horn and then go out through a wire to your computer. And of course, like I said earlier, usually this whole thing is in a vacuum chamber. So this would not work at atmospheric pressure. Your ions would just not be able to make it through because all the gas would get in their way. And so this is usually just sealed off and pumped down to real low pressure. All right, now let's get to our very last type of mass spectrometer. The reason I'm doing this last is because in this technique, which is known as Fourier transform, you actually detect your ions and separate them at the same time. So we're going to talk about a technique, a specific instrument in this technique family called Fourier transform ion cyclotron resonance mass spectrometry, or FTICR-MS for short. So our department has, I believe, one working FTICR instrument right now. But the way this works is you just have a magnetic field. This is usually a very strong magnetic field, a couple thousand times the strength of the magnetic field on the Earth's surface. And like I said before, if an ion gets into a magnetic field, just one of the fundamental principles of physics is that ion will start to orbit that magnetic field. So if we have a magnetic field line running through here, the ion will circle around that. And then whether it's a positive ion or a negative ion depends on whether it circles one way or circles the other way. And that just has to do with the right-hand rule or left-hand rule that you should have learned about in physics. And if you didn't, I'm sorry, I'm not going to go over it today. But what we get in this FTICR instrument is a orbital frequency. So all of the ions are orbiting basically with the same radius, but the amount of times it goes around that magnetic field line per second is actually proportional to the mass to charge ratio, or more specifically to the charge to mass ratio. But that's basically the same thing. So you just have to divide the frequency, or take 1 divided by the frequency to get this into mass to charge. And then we have detection plates on top and bottom of where these ions are orbiting. And so as the ions come close to this detection plate, the detection plate can see them. So if it's a positive ion coming towards this detection plate, that'll cause electrons to flow down through a wire into this detection plate. And if it's a negative ion coming through, that'll repel the electrons in this plate, so you get a current going out. But then as the positive ion moves away, the electrons no longer have a reason to stay there, so they'll leave. And if the negative ion drifts away, then the electrons that left the detection plate no longer have any reason to go away, so they will come back. And so what we're actually measuring here is a flow of electrons to and from this detection plate. So that's just the current of electrons going in there. And just to clarify, you can't have both positive and negative ions in the FTICR at the same time. It would only be positive or negative. And with the FTICR-MS, you can actually get the best resolution of any mass spectrometer out there. But one of the really complicating things about this is usually you don't have a single ion or a single species in here spinning all at the same frequency. Usually you have multiple species, and they're all spinning at different frequencies. So if we're getting a different frequency for each ion, we get something like this, where one ion would give us a frequency or a sine-looking wave that looks like this. The next would give us a frequency that looks like this. A third might have another frequency that looks like that. And what we're going to see on our detection plate is the sum of all these waves. So we'll see something that looks like this. Now, what do you do with data that looks like this? This is almost useless, you might think. Well, that gets us into what a Fourier transform actually is. So a Fourier transform is a mathematical process that you can use to apply to data like this to get back out the individual frequencies that come together to get that. So even though we can often have hundreds of different species or even thousands of species, each giving a different frequency, we can send this through Fourier transform and get back out all those individual frequencies. And so some scientists in Florida have actually been able to use FTICR to resolve, I believe it was somewhere around 10 to 50,000 different species in crude oil all at the exact same time in an experiment that took roughly 1 to 5 minutes to complete. So FT instruments are ultra high resolution instruments, and they detect all of the ions all at once at the same time. There's another instrument, another FT instrument called the Orbitrap. So the Orbitrap is a lot like the FTICR, except instead of a magnetic field, it has an electric field, and so the ions spin around due to an electric field rather than a magnetic field. We currently have 4 or 5 Orbitraps in our department. All right, so we've talked about how mass spectrometers worked. We've talked about how to get ions ionized, how to get them into the gas phase, how to select for mass to charge, and how to detect them. Now that we've done that, let's look at what we see on the computer and how to make sense of it. We'll start by just looking at alanine, one of the simpler amino acids. And so alanine here has a molecular weight of 89.0932. However, when you put alanine into a mass spectrometer, you get a mass spectrum that looks like this, where you have a peak at 89.0477, one at 90.0510, and a third that's usually really small, but sometimes you can see it at 91.0519. So these are our different isotope peaks. But you'll notice that none of these add up to or are equal to 89.0932. So why do we get this value? Well, it's because this is the average value of all these peaks. So 89.04 is the most abundant, 90.05 is the next most abundant, etc. And so if we take this mass, times it by the height of each peak, and then take the average of all that, then our molecular weight on average will be 89.0932. So that is the first thing to know, but then I'm going to tell you we can actually also get a lot more information out of this peak right here. Why is that? Well, because it is the sum of different isotope masses, namely carbon, hydrogen, oxygen, and nitrogen. And we know all of the masses of all the isotopes of most of the elements really, really well. And so if we take all of these masses of these different isotopes, there's actually only a single way to add all these up to get 89.0477. And that only way is if we take 3 carbons, 7 hydrogens, 1 nitrogen, and 2 oxygens. There are actually no other possible combinations of isotopes that you can put together, including transition metals, noble gases, or anything else that you can put together that'll get you a mass of 89.0477. So this is what we call the exact mass, and the exact mass can give us the exact empirical formula here, right? And so it tells us the formula, and you can actually do this up to about 600 AMU. Above 600 atomic mass units, usually the resolution and precision and accuracy of your mass spectrometer make it so that it's less easy or less simple to get empirical formulas from exact masses. Above 600 up until about 1200, you usually get good information that can give you a slight handful of different possible formulas. But above that, you really don't get much in terms of mass. And that's because above that, there just become too many possibilities that can add up, and there's too much uncertainty in the exact mass to get an exact empirical formula. Additionally, this exact mass doesn't tell us the structure. So it doesn't tell us that this is alanine, it just tells us that these elements are all in there. So there's a couple different ways you can imagine of arranging these to get a molecule, and it doesn't exactly have to be alanine. So how do we get the structure? Well, this goes back to electron ionization or chemical ionization, wherein we get fragmentation patterns. And these fragmentation patterns, they aren't just completely random. There is some logic to how they are broken down. We're not going to go through that logic today. I'm just going to give you some examples of how this works. So for example, right here, I have decane, and this is the mass spectrum for decane obtained with electron ionization. You'll notice there are some discrete peaks out here, and these discrete peaks actually correspond to different fragments of decane. So this first one here is loss of 2 carbons. We don't see much of a peak or any peak for loss of a single carbon. But here is loss of 2 carbons, loss of 3, loss of 4, loss of 5, loss of 6, and loss of 7. Now, interestingly enough, we also see the 2 carbons over here that are lost from this fragment, right? So if you take decane and split it right here, you're going to get this fragment and this fragment. So why then is this fragment more abundant than this one? Well, the reason is because only one of these fragments gets charged. The other one remains neutral. So it's a good probability that you're going to break this decane molecule right here along this bond. And it's a really good probability that this 2 carbons over here will take the charge, and this side will remain neutral. There is some probability that this side will take the charge, and this guy down here will remain. And again, we don't have a peak over here for a loss of a single carbon, because that's just low probability. All right, but let's compare this fragmentation spectrum for decane to another fragmentation pattern that we get for another molecule with a formula of C10H22. This time we're going to look at 4-propyl heptane. So in this case, we get a very small peak for the intact molecule. Then we get some very distinctive peaks. So this one is for loss of 3 carbons. So that would be a loss of a single one of these branches. And then we get some other peaks for losses of different numbers of carbon. But you'll notice that the fragmentation pattern for the 4-propyl heptane looks a lot different than the fragmentation pattern for decane. And this isn't even a very dramatic example. In this case, we still have peaks at very similar positions, just with different abundances, etc. Some species with the same empirical formula, but drastically different structures get drastically different mass spectrum. All right, so now we know about exact mass, we know about fragmentation patterns. And there's also a little more information we get from these mass spectra in terms of isotope patterns. So of course, different elements have different isotopic ratios and have different numbers of isotopes, different distances between isotopes, etc. So carbon, its isotope pattern just looks like this, where most of it is carbon-12, and you get a very small amount, less than 1%, that is carbon-13. And then you have other species like chlorine and bromine that have really unique isotope patterns. So for chlorine, chlorine's got 2 isotopes, chlorine-35 and chlorine-37. Chlorine-35 is about 3 times bigger than chlorine-37 because chlorine-35 makes up about 75% of chlorine, and the 37 makes up about 25% of chlorine. And bromine, which is right below it, it has 2 isotopes, bromine-79 and bromine-81. And so on the periodic table, bromine actually comes in at around 80, or a little less, it's 79.9 something. And that's because bromine-79 and bromine-81 are really close in abundance. 79 is slightly more. And I should point out too, just in case you didn't catch that, the isotope peaks for chlorine are also 2 mass units apart. So it's chlorine-35 and chlorine-37. And then we have bromine-79 and bromine-81. And so whenever you have isotope peaks that appear to be 2 mass units apart instead of 1, it's usually a good sign that there's some chlorine or bromine in there. And of course, there's lots of different elements, and each element has its own isotope patterns. except of course for elements that only have single isotopes like cesium. And some of these isotope patterns actually get really complex and fun. So for example, this is xenon's isotope pattern. It's got 1, 2, 3, 4, 5, 6, 7, 8, 9 visible isotopes, and it's actually got a couple others that you sometimes see that are radioactive with a long half-life. So we actually get a lot of information from our mass spectrum. Right? So to see if you understand this isotope pattern stuff, here is a practice problem where I want you to match each of these chemical formulae to their mass spectrum over here. So go ahead and pause the video real fast and see if you can figure that out, and I will go over the answers in a second. All right, so let's look at these species over here. They all have different formulas, and so they actually all have different molecular weights. And so one way you could solve this problem is just by calculating the molecular weight or average molecular weight of each of these just from the values on the periodic table. And if you look, this peak's coming in at about 124, this one's coming in at about 90, this one's coming in at about 80. So just calculating their average masses would be good enough that you'd be able to figure out which of these was which. Another way that we could do this, though, a simpler way, is by looking at their isotope patterns here. So you'll notice this species has chlorine, this one has bromine in it. So for chlorine, if we only have one chlorine, then we should have one peak that's relatively large, and then a second peak that's 2 mass units away that has a height of about 1/3 of the first peak. And so if we look at these, we get that right here where we get a big peak, and then we move over 2 mass units and we get another peak that's about 1/3 of the height. So we can immediately identify this spectrum as coming from the species with the chlorine in it. I want to point this out too. You'll notice there's a little peak right here, and if your computer is really high def, you'll notice there's a second peak over here. These are actually still from this C2H6NCl species, but these peaks are resulting from C13 isotopes in there. And this one is actually resulting from a C13 and a Cl35 isotope in the same molecule. And of course, there are some slight contributions from deuterium being present or from heavy nitrogen N15 being present, but mostly that's coming from carbon. All right, so we've identified the chlorine-containing species. Now let's try and identify the bromine-containing species. This will be a spectrum where we have 2 peaks of relatively the same height, and the 2 peaks are 2 mass units apart. And we have our little peaks down here coming from our C13 or our deuterium, etc. And so this is coming from our species C, and then we can identify this one by process of elimination as coming from species A up there. Mass spectrometry is a really powerful technique in and of itself, but when we couple it to other techniques such as liquid chromatography or gas chromatography, it becomes even more powerful, because now we're usually separating them by polarity or other physical properties before sending them into the mass spectrometer to be analyzed. And so now we're not just separating based on mass to charge, we're separating on polarity and mass to charge. So since we're screening based on 2 criteria, we get a lot more information about our species. So I'll give you an example of what some data from an LC-MS coupling looks like. And we'll do that by looking at an analysis of some street heroin. And for those of you that might know this by a different name, street heroin also goes by the name of smack, H, big H, tar, dope, hell dust, horse, junk, chiba, brown sugar, mud, China white, white nurse, white lady, white horse, white girl, white boy, white stuff, he, boy, brown crystal, Mexican brown, Mexican mud, snow, snowball, skunk, thunder. And it also comes in the black tar varieties of black tar, black pearl, chiva, Mexican black tar, Mexican tar, and negra. All right, so let's look at some analysis here. What I have up here is a chromatogram obtained from LC-MS of some street heroin, and you'll notice there are several peaks in here, indicating that this is not just street heroin. So if we select for M/Z 286, we actually can just isolate this first peak right here, which corresponds to morphine. Now you got a little bit of morphine in there, a little painkiller. We select for M/Z 300, which is this second peak, that actually corresponds to codeine. This third peak right here is actually 6-acetylmorphine, which is a derivative of morphine, and it shows up at M/Z 328. This last peak right here, or this big peak, you might think is your heroin, but of course it is not. It is papaverin, which dilates blood vessels, might make your heroin rush a little more intense, but it is definitely not what's getting you high. If we get to this tiny peak over here labeled as F, there is your heroin. Then the peak after heroin is acetylcodeine, and then the last peak is called noscapine. Now, noscapine is a cough suppressant, and of course, as all of you know, if you have heroin mixed with a cold medicine, that is known as cheese, right? So this is not actually street heroin, black tar, H, or white lady. This is cheese, and it's not very pure stuff because you got all this other junk in there too. So this is a bad supplier. Maybe a different supplier is required. But in all seriousness, this illustrates to you the power of LC coupled with MS altogether. And this is actually not a very complicated sample of street heroin. You can actually get way more dirty street heroin where you end up with hundreds of peaks. Usually those other peaks aren't other drugs or additives. Usually they're just contaminants from whoever made the heroin being really messy, not washing their hands, using dirty glassware. Maybe there was some bacteria in the glassware they were using, so it can get really, really nasty. You can really get people sick. All right, but in summation, you can use your mass spec library to determine the ID of an unknown species. And so your library can look at the chromatography retention time of your sample, can look at the exact mass, isotope patterns, and fragmentation patterns. So you combine all of that and you can actually get lists of hundreds of thousands of species that you can use to identify unknowns with. And so vast numbers of small molecules have been identified and run through these mass spectrometers using electron impact ionization and other sources as well, other ionization sources as well. And so you're able to actually identify a lot of things with this really simple experiment using mass spec coupled with LC. If I give you these following two equations, can you derive an equation that relates mass to charge in a time-of-flight mass spectrometer? Specifically, an equation where you have mass to charge on one side and everything else on the other. Go ahead and pause the video and see if you can solve for that. All right, so here's how we'll do it. We'll set QE equal to 1/2 mv squared. And of course, we'll remember that v, our velocity, is equal to distance over time. And so we can make this substitution of length divided by time and put that into our equation. Then it's a matter of just multiplying and dividing to where we get mass divided by charge is equal to 2e times t over L squared. Make sure you can reproduce that derivation. Next question. Which is bent more by a magnetic field, a light ion or a heavy ion? So if you have two ions traveling through a magnetic field, they're the same charge. Which is going to be bent more, the light ion or the heavy ion? Go ahead and pause that and think about it. It is going to be your light ion. So your light ion has less mass, and so it's easier to change the momentum of your light ion. Next question, what does the RF destabilize in a quadrupole and how? Go ahead and pause the video and think about this one for a second. All right, hopefully you remembered that it is light ions that are destabilized by the RF. This is because the RF causes ions to spin, and the lighter ions have larger orbital radii, and so the ions with too large of a radius, meaning the ions that are too light, will collide with the quadrupole. Remember again that this is heavy and light, not big and small. We're not dealing with size of our ions, we're dealing with the charge on our ions, or more specifically, the mass to charge on our ions, right? We care about mass and charge, not about size. which has a lower rotational frequency in an FTICR instrument, calcium 2 plus or sodium plus? Go ahead and pause the video now and see if you can't figure this out. Now for this problem, you do have to look at a periodic table. You have to know the masses of these two ions. All right, so the mass to charge ratio of sodium plus is equal to 23, which is the mass of sodium. And of course, I am simplifying that a little bit just because I don't need it to be more complicated for the question I'm asking. So we have 23 divided by the charge on sodium, which is 1. So we have a mass to charge ratio of about 23 for our sodium. Then for calcium, it has a mass of about 40, and it's got a charge of 2, so it has a mass to charge ratio of 20. And so calcium 2 plus will show up at a lower mass to charge ratio than sodium plus. And so now the question is, which has a lower rotational frequency in an FTICR instrument? Now to answer this part, I don't know that I necessarily gave you enough information yet, but you should know that ions with a heavier mass to charge ratio are going to be moving more slowly. That means they're going to be orbiting that magnetic field line, taking more time, which means that they're going to be moving more slowly, and they will have a lower rotational frequency than the calcium 2 plus. That is it for our lectures. Feel free to contact me as you review for the final exam. Let me know what questions you have. Of course, the final exam will be during finals week as normal.